Hello, my name is Richard Thomson, and for the past year, I've been working on a project with Dr. Ribaudo about the construction and use of a radio telescope. All right, so before I started creating the system, I had to make sure it was going to be designed optimally. So because I knew that the signals I wanted to collect were going to be were right-hand circularly polarized signals that came from the NOAA and other weather satellites, I wanted to create a double cross antenna design that looks like this. And this was going to be the best design because I knew that it gave equal exposure to the incoming signals, no matter which orientation it was in. So whenever the satellite's flying above the Earth, it's going to be collecting the signals at all instances of it, like no matter where it is. And then this design down here is going to be the ideal radiation pattern collected during this design. So we can see that at all spots, it's relatively high. Like there aren't any significantly low spots. Like it's all pretty strong no matter where it is. So also going along with the preliminary design stuff, I had to make sure everything was going to be to the right parameters. So the signals I wanted to collect came from the NOAA satellites, as I had said earlier. And because I knew that the streams were going to be emitted at 137 megahertz, I was able to use this chart to get information on how to build my system. So the dipole length, which is the length of each antenna itself, had to be 38.25 inches. And the diameter had to be roughly 0.375 inches, and the spacing between each dipole had to be 21.5 inches. I'll explain this later on, but I had a problem with the dipole diameter parameter right there at the beginning, but I had fixed it later on. So to build the whole structure of the system, this was my first like actual design step right now. So I initially wanted to use wood, but I eventually found out that using a wood design would definitely not be optimal because it just wasn't as stable as I wanted it to be. And it also wasn't going to last as well if I brought it outside, because my initial plan was to leave this outside and be able to collect data whenever I wanted. So the first step I did was cut out the PVC piping for each antenna's leg carrier. And then after that, I wanted to cut a long piece of antenna for the base. So the four legs I was talking about before came from this table right here. So I made each of them roughly 21.5 inches long. And then, or I made it so it would be 21.5 inches between each one. So half of that. And then I wanted to cut a long piece to make sure that it would be above the ground pretty high so it wasn't going to pick up any extraneous signals. And also, whenever I was deciding on the PVC to use, I realized that I definitely wanted to use thicker PVC so I could fit all the cables inside of it that I needed to fit. And this was the final picture of what my base looked like. So after I built the base, I wanted to design what the cable network looked like. So I had to begin by cutting out all of the 5 coaxial cable pieces I need, one for each dipole, and then one where all of the dipoles would come together and go through the base into the software-defined radio, otherwise known as a SDR. So I had to follow this schematic right here, which I found online. And I found out that I had to account for phasing differences by making the wire for dipole 3 and 4 1/4 of a wavelength longer than dipole 1 and 2. And then from there connected into the main wire that went through the base. So after I had the internal wire network designs, I had to start worrying about the antenna system itself, like the actual dipoles. So as I said before, I had an issue with the diameters because I used very galvanized wire. And I think it's kind of obvious why this wasn't going to work out. It was just very thin, but I'd heard from another source online that it would still collect signals and it was cheap. So I went with that initially. But I later found out that it just wasn't going to work. So I had to switch to getting dowel rods of the right parameters that I said before. So an issue I had with the dowel rods is that it was really hard to connect it onto the base and have electrical signals. So I came up with this system right here where I wrapped the rod itself in foil and then put an insulation wrap on the outside of it. And then in between the insulation wrap and the foil, I stuck pieces of coaxial cable internal wire inside of it just to make that electrical connection. And then I would later solder that piece of wire sticking out onto the other cable network to get it all connected. So after that, I was able to attach each of the 4 metal dowel rods onto the whole system. And so as I said before, I would solder each of those little wires right there onto the wires that were inside of these long PVC pipes right there. And then to secure the whole thing, I duct taped it all together. And I made sure that it was all at a 30-degree angle tilting downward. And this went along with the design of the whole system because that 30 degrees accounted for differences in position of the satellites. And then, so after my system was completely finished, I took the wire into the SDR, or the software-defined radio that I explained earlier, and that was able to go into the computer. And running that signal through a program called GQRX, I was able to track the signal and make use out of it. However, I didn't get to this point because we were going to collect data on the coming weeks. Like we were going to be doing that in the past couple of weeks from now, like after spring break. But unfortunately, I wasn't able to get to that point. And this data right here was just from the research room we were in using a different receiver. And so anyways, after I would have theoretically collected the data on it, I was going to be able to run it through Audacity to sample it and just kind of prepare it, like slow it down and prepare it, whatever, to make sure it's all good. And then after I would have that signal be finalized, I would have been able to run it through a program called WXM to IMG. And this program is really interesting because it decodes all the information that's stored in the signal and turns it into a colorized image. And that colorized image would have been a map of the Providence area. And so as I mentioned before, I wasn't able to get to this point because of the coronavirus shutdown. But I hope that other students in the coming years find interest in this project and want to carry it on. So, yeah. Also, another important thing to mention here is that I would have had to use a program called Orbitron to determine when the satellites were passing by. And to end with, these are some final pictures of the overall product. And this down here is where, the wire snapped, but this is where it would have plugged into the software-defined radio. And then this is the software-defined radio itself. All right, and that is all. Are there any questions?
Thank you so much. That's really interesting work. We do have one question that came up, and it was, why did you decide to build a radio telescope in the first place?
So I thought it was really cool. I heard that Dr. Ribaudo was doing research on it in general, but they were doing a project that was with Arecibo, and it's a really, really big radio telescope. And they were using it to observe different galaxies and stuff. But I thought it would be more interesting to work on it from a different angle. So I wanted to build my own radio telescope because that's a project that he's doing with another student. But.
Yeah, and I think you mentioned that all this stuff, all these materials and what you built will be available to future students. Are you hoping that somebody else takes up this project and they'll use it as well?
Yeah, I really hope so. Like, I built this for something and I hope it gets used, and I would do it next year, but I'm transferring out this upcoming fall.